Hello friends, in this video I'd like to solve the following problem from William Lowell Putnam Mathematical Competition 2010 Problem B1. The question is there an infinite sequence of real numbers a1, a2, a3 and so on such that a1 to the power of m, a2 to the power of m plus a3 to the power of m and so on equals m for every positive integer m? That is the question. So my hints for this problem. Let's suppose that there is such a sequence, a1, a2, a3, and so on. And ask yourself these three questions. Can ak have an absolute value greater than 1 for some k? Can it be? Then, second question, can ak have absolute value of 1 for infinitely many k's? Can it be? And finally, can ak, absolute value of ak, be less than 1 for almost every k, apart from finitely many? After answering these three questions in this order, you should be able to say if such a sequence exists. So give this problem a try and I will see you in a minute. Okay, so first of all, so as I suggested, let's suppose that there is such a sequence. A1, A2, A3, and so on. Okay, and now, first question was, can it have some number greater than or equal 1 in absolute value? So, suppose that, I will say that it's impossible actually. Suppose that, let's say, k has absolute value greater than 1 for some k. Can it be? Well, let's take a look. Then that would imply that a1, let's take only even powers. We'll be dealing with even powers. Somewhere along the way, they will be ak to the power 2m and so on. Well, this sum, well, since we are taking even powers of real numbers, they are positive, or non-negative rather. So this number, this sum, is obviously greater than or equal ak to the power 2m. But obviously, it should be obvious that this is strictly greater than 2m for sufficiently large m. For sufficiently large m. Well, why is that? Well, it's a well-known fact that exponential function grows much faster for big arguments than linear function. Of course, exponential function with base greater than 1, and we are now just supposing that the absolute value is greater than 1. So, well, it cannot happen because this sum actually should be equal to m, and it turns out that it's strictly greater than 2m for sufficiently large m. So we have a contradiction. Cannot happen. Okay, so now we know that our numbers must have absolute value of less than or equal 1. Second things, can it have absolute value of 1 for infinitely many terms? So suppose that now ak equals 1 for infinitely many positive integers. Can it happen? Well, no. Why not? Well, because already a1 squared plus a2 squared plus a3 squared and so on, we are taking non-negative integers, and in this sequence there are infinitely many numbers 1. So in fact, under this assumption it must be plus infinity. well, it should be equal to, so it's impossible. So we have another contradiction. Okay, so what we now know? Now we know that in our sequence there cannot be numbers with absolute value greater than 1, and moreover, absolute value of 1 can be attained only finitely many times. Only finitely many times. So the last supposition, so now suppose that AK equals 1 only for finitely many indices, and let's say AJ is less than 1 for every other indices J. Well, what happens now? Let's take a look. Indeed. Well, here we have another problem. Because if we take a look at our sum again only over with even exponents, it should be equal to m. Let's remember that. Well, here we have another problem, because this sequence right here, this function is decreasing as m increases. Well, why is that? Well, we have a bunch of ones in our sequence, so they stay the same. And every other number has absolute value of less than 1, and we know that the higher the exponent, the less the number. So it's decreasing, strictly decreasing, while this function is increasing as m increases. So again, we have a problem. It cannot happen. Another contradiction. Well, and that says there is no other option. So the conclusion is our sequence cannot exist. So it's our answer. So there is no such sequence. There is no such sequence. And that closes our problem. There is no such sequence. Let's make a better shape. Here it is. Okay, pretty nice problem, I'd say. Thank you for watching, and I will see you next time. Goodbye.